Do I need to mute? I should mute this, right?
It's up to you. It doesn't matter. And then just put slide in. I mean, sorry. Yeah. Is there anything in this lecture that you see? He's a friend of one behind here. He usually shows up.
Yeah, usually go at least one teammate.
You guys should donate in the live chat. Some money.
Oh, this is the money we're doing too.
It goes to Alvin.
It goes to Alvin.
Yeah.
He's gonna hire more ML lecturers so we can do more. Can do one every single day.
Yeah, every day.
Every day for 2 hours. And then eventually we hire Vincent. I would work for Vincent, bro, if he took control.
You already work for him.
That's true.
During class, so I don't want people. Oh, yeah. Yeah, it would be fun to say. So staff and lots of fun. I feel like it'd be really cool. Kind of stuff like serving food and serving drinks and saying hello, thank you, you're welcome. I don't know. It was fun. It was like fun. Oh my gosh, there's so much food. And the pizza that was left over. Yeah, definitely. And we were like, hey, there are some boxes.
Yeah, the breakfast.
I have like for the week, you know. Are you computer science? That's really cool. Yeah, I mean that's very interesting. And it's the first college, like the major research out of it. So it's very, very fun and new. But it's fun. But I mean, it really looks like computer science. Yeah, I can imagine. Probably just like computer science with like, you know, a little bit of extra. Like, yeah, definitely. I have algebra. I have calculus, data structure. Yeah, a lot of things similar. Yeah. We have some subjects like visual image processing, computer vision, and signal processing.
Do you find any?
I've tried to. I really like that. Yeah. At UF, like we don't have that yet, but we have like the artificial intelligence certificate. But it's like the certificate. Yeah, it's cool, but it's like it's geared towards all majors, so you don't really go really deep into the background of AI. It's more just like here's how you can apply AI to your field. So it would be cool to have something like that here. Yeah, definitely. But I mean, what we understood, there is very
unmute this. Hey guys, so this is the seventh ML Monday. Last week I think Alvin did deep neural networks, training deep neural networks, training neural networks, not deep neural networks. Today we're gonna do training deep neural networks. So just a little bit of review from before, as well as some new stuff. We're gonna do a little bit of a demo with some MNIST data, which is basically handwritten digits. We're gonna try to classify them into what digit each specific image is. And then, yeah, I mean, I have a couple of visualizations that are pretty cool. So we'll see how that goes. But if you want to sign in, you can sign in now or you can sign in at the end of the lecture. Just again, a little bit of intro. I'm Kartik, one of the MO lecturers. This is my first MO lecture, so you guys haven't seen me before. If you have any questions, anything related to ML or link, like anything, you can reach out us on email, LinkedIn, anything. We'll be happy to help. That's why we're here. But moving forward, okay, so review of previous lectures. What do you guys remember so far? Like anything from any lecture?
Gradient descent,
Gradient descent, okay. What else do we remember? Yeah,
neurons,
neurons. Mm-hmm.
mean squared error,
Mean squared error, okay. What else?
backpropagation,
Backpropagation, okay. I like it. Anyone got anything else?
loss,
Loss functions, that's pretty big. What else? Yeah,
dot product.
dot product, yep. Nothing else? Okay. So just what is a deep neural network? I mean, it's basically a neural network, but you have two or more hidden layers, and that's why it's considered deep. I mean, ResNet 18, which is a common image classification architecture, has 18 layers, hence the name ResNet 18. I mean, you have a couple other architectures, ResNet 34. I've been working with some of them in my research lab, so those ones are pretty cool. You have GPT-2, which is a prior open source version of the GPT models you guys are familiar with. That one has 48 layers, right? So, I mean, those ones have a lot of layers. They're very much so more than just deep. They have more than two or more hidden layers. We have a little diagram here with our inputs. We've been over the weights, we've been over the biases, our activation functions. It doesn't have to be, every layer doesn't have to be connected to each individual layer, but here you can see we have all the neurons are connected to everything in the following layer and all the layers and the ones in the previous one. Let's go through a little quick demonstration that I found for you guys to kind of show how like a model learns, right? So here we've been over learning rate. I mean, that's the rate at which your model learns. So right here we have let's say we have a learning rate of 0.03. This is a common activation function, ReLU. Regularization, you can do L1 or L2. We'll go over that a little bit today. That's basically making sure that our model isn't going wild with what it's doing, right? If you have a model, we don't want to overfit it, right? We don't want it to memorize the data, and we want it to be able to generalize, make judgments off of the data. So that's what regularization is kind of having these limiters or these kind of like assistances on these model, right? So for right now, we can just leave that there. We'll have a classification problem. And let's say we have a data set that looks something like this. And if we have 4 neurons, and let's say 2 hidden layers, so this is automatically a deep neural network. We train it. You guys can see how the decision boundary forms, right? I mean, we're not realistically going to be training a model for 300 epochs, but you see the blue region, that's our decision boundary of the model. And basically, I mean, if you look at our test data, we're getting all of it right. And so if we want to opt into something more complex, you'd see that trying this is not really going to work, right, the way we want it to. I mean, our loss isn't decreasing. If you look at our decision boundary, it's just half and half. And so if we see the trend where we add more neurons, we might get a better loss based off of how that logically works. Not really, actually. What if we add more layers? Let's see. Change the learning rate, move it up a little bit. We add more training data, right? We don't need 50% of it to just go straight away to testing. increase the batch size. These are some standard things. Regularization, I'll go over it in a bit, but actually we might not need like that. Let's leave that right there. Okay, this is embarrassing, it's not working. Okay, I should have a better decision boundary. I mean, it's decreasing. We're getting somewhere. Let's bump up this to like 0.1. See? Right, so we kind of see a trend. We're just trying to capture the little spiral. I mean, let's pause it right now. Before it was just like 0.5, right? I mean, there's still a lot of work to be done, but this just kind of shows you the different ways you can play with models. I mean, we just added more layers, more neurons. We just like did some of the basic stuff, right? We're playing around with our learning rate, moving it up, moving it down. And we already see that the loss has decreased to like 0.272 with our test data set, right? And so this is just kind of a basic overview of how neural networks work. I mean, this is a classification problem. I mean, you could change this to something like regression, right? If you want to look at that. But going back to the slides, I mean, yeah, so that's neural networks right there. Hyperparameter tuning, does anyone remember that? Or like, does anyone have know what they remember from that so far yet? No? Okay. So hyperparameter tuning is basically the process of how we set the parameters for how the model learns, not what it's actually learning, right? So again, going back to our learning rate, our optimizer, which is how the learning rate updates, our batch size, which is how much data we're training on each iteration, our number of epochs, how many iterations of the data we're training, whether our model is going to be deep or shallow, deep, more layers, right? We already saw that with our little visualization right before. If we added more layers, that helped a lot. A shallow network is usually not that good. And then there's two other things, funnel approach and stretch pants. The funnel approach is ideally, we kind of want to have this rule of thumb that as the model architecture is built, we want to have less and less neurons in each layer as we move forward, right? So our first layer can have 128 neurons. The second layer, we want to aim for something that's less than that. So ideally something like 64, 32, and then we want to, each layer, we want to get less and less neurons right there. So that's the funnel approach. We kind of want to make it look like a funnel. Stretch pants is we want to have this thing called dropout, where at each layer, we have this type of regularization called dropout, where we drop out neurons from the layer. And I'll go a little bit more into that later, but that's also a way in which we want to have like a good neural network architecture, right? And then we have vanishing gradients. So during training, the gradient vector, which is basically how we're updating the model, right? It can get extremely large or it can get extremely small during backpropagation, right? And if it's extremely small, that's not really useful for us because that's going to be difficult to update the weights because we don't really have anything to go off of because the gradient, again, is very minimal, right? So we can have some strategies. We can have a weight initialization method where we start off with a set amount of weights. We have non-saturating activation functions, functions that don't really have this problem, right? Like dying RLUs. A neuron can die when it's weighted, some of the inputs are negative. And in this case, the RLU would input to 0, right? So that's one way we can resolve that. We have leaky RLUs where if it's like, okay, it's always going to be outputting something regardless of if it has like some sort of vanishing gradient issue, right? So the best way to fix that is we want to look at our loss function, how we're doing our batch normalization. We can also add gradient clipping, which is if we have our gradient going too high, if it's going like crazy, we want to clip it to a certain value. So we're not just oscillating in our loss kind of function and we're just kind of smoothly diverging. So basically, main takeaway from vanishing gradients is look at our optimizations and how we're doing our loss function and how we're doing that. So, okay, bias and variance. So bias is basically the idea that we have a model, right? And we can't understand the right relationship because we have these underlying assumptions. I mean, if you look at the diagram on the right, we have this regression illustration right here, where we have kind of like a parabola. This is what our training data set looks like, but we're fitting a model that looks like a line that's just going like that, right? So there's a sense of bias in that we're not really making the right assumptions to kind of curve it correctly. That's the issue with bias, right? And then we have variance, which is easier to understand. That's the sensitivity of the model to minor changes in the data. right? So if you look at it on the right here, I mean, for every single data point, you're seeing that the model kind of just shifts a bit, right? And we don't want that sensitivity because in the test set, we're gonna have a lot of that variance too. And we want it to have more of a generalization aspect than just kind of just have sensitivity like that, right? So here's another illustration with classification with bias. This is not really perfect. We have a line that's just going straight through, not kind of being specific enough. We need more information or more parameters with that. This is, again, these two are perfect. And then here with classification, we have a line that just goes everywhere, right? We're not really classifying. At this point, we're just memorizing and just having a crazy amount of sensitivity. And what that will look like with our deep learning illustration, right, is our validation curves, right? If it's high bias, we're gonna have both our validation and our training curves to have a high loss, meaning that nothing's really going on, nothing's really learning. When it's good, it's gonna converge nicely into a low value. And if there's variance, you're gonna spot that if you see that our validation error actually shoots up way higher than our training loss, right? So as you see right here, there's a huge gap. And what that means is, again, we're overfitting. We're having a large amount of sensitivity to our data, right? And when it comes time to test it through our validation iterations, the model's not reacting properly and we're getting a lot of errors with that, right? It's a little small here on the bottom, but the best way to fix that, what is it? Underfitting? Yeah, underfitting, which is basically high bias, is you want to complexify the model. You want to add more features. You want to add better, make it more complicated. I mean, as you saw with the little demonstration at the start, that data set with the spiral was way too complex to just have 2 layers, right? So as soon as we added more layers, more neurons, we added more complexity, we start to see that the model is getting better, our performance is getting better, right? Adding more features, that kind of ties into that, and training for a longer amount of epochs. I mean, this is usually, I mean, it's going to sound intuitive. If you train it longer, it's going to learn better. But especially in the case of bias, we want it to train longer so that actually the correct patterns can be understood. We don't want to stop early with that. And then we have overfitting, perform regularization, which is I'm going to get into right now very soon. And then we have get more data, right? Right now you see there's an increased amount of sensitivity that would intuitively go away if we add more data, right? To kind of just average off of and kind of see better trends, and the model can learn in a way where it's not just memorizing, it's actually learning the specific trends right there. So that's with bias and variance. Okay, getting into regularization. So we had the issue with variance and everything. One of the best ways to regularize neural networks is early stopping. It's very easy to understand, right? So if we have something where the model starts to overfit, right, we're going to start to see a trend where the validation error is not going to go like down necessarily, right? When we're testing the model through our training process, because that's what the whole point of the validation curve is, right? Once we start to see that we're done enough, right? Our curves like this, right? We don't need to like keep training it more. We can stop early, right? We can just stop the model right there, right? So if I can maybe just kind of zoom in, is there a loss diagram I can show? So like right here, this curve right here, once we start to see, okay, it's plateauing nicely, the validation curve and the training curve are right here, right? We don't have to necessarily go the full way and risk overfitting, right? We can just stop early, whether that's 5 epochs early, something that's going to be dynamic, and within our training procedures, like, oh, okay, our loss is increasing for 3 iterations, now we can stop it. That's what early stopping is. We have L1 and L2 regularization, which are a little more complex. We have L1, which is basically we're going to drive some weights in the neural network to exactly 0. We want to limit the amount of features we're actually using to make predictions, right? We don't want to use everything and then risk overfitting. L2 has a similar idea with playing with the weights, but this time we're going to shrink them smoothly, and we're basically discouraging large values and having a sense of kind of, I guess, clipping to the weights. And we can combine them both actually to kind of get elastic regularization, and we get even more balance with that. And I mean, this all sounds nice with regularization, but again, we also don't want to overdo it, because I mean, if we stop too early and we regularize too much, what are we gonna have? We're gonna have something with a bias, right? We're gonna have a high bias, right? So it's kind of like a little bit of a negative relationship with those two. You don't want to have high bias and low variance or low bias and high variance. You want to kind of have a mix of low for both of them, right? And then the next thing is max norm regularization, where we constrain each neuron's incoming weights, right, to a certain hyperparameter R, which we learn through our hyperparameter tuning. And after each update, weights are rescaled if they exceed R. So it's kind of like clipping those weights, not added to the loss. It's applied as a post-update constraint. And then we have dropout, which is what I talked about earlier. So during training, we have certain neurons that might be ignored, right, with the probability P, right? And what this does is it prevents co-adaptation, right? We want each neuron to kind of have its own independent influence in the output. If all the neurons are kind of like co-adapting together, what we're doing is we're risking overfitting again, and we want each neuron, so like if we drop it, it can still generalize. We want our model to remain simple off of the feature extraction and what we're predicting, right? So that's what the whole point of dropout is, right? At inference though, when we're actually making the predictions, no neurons are actually dropped. Weights are scaled to compensate. But I mean, again, P is a hyperparameter, so dropout rate is usually around 20% to 50%. And yeah, I mean, you're gonna see that a lot, especially in the demo that I'll be showing later. And then, okay, does anyone have any questions so far yet that I would, yeah.
Could you explain again what clipping is? I know you kind of did before, but
Gradient clipping?
yeah, I guess.
Okay, yeah. So when we have like our gradients, right, we're using them to train the model. If it gets like too high, right, we don't want it to like every time just like kind of in a way just go through with that, because then we're just gonna get like a click curve where it's like it's optimizing it too much to the point where it's going in the other direction too much. And so gradient clipping is we're clipping it to a certain value, right, and kind of restricting that. Yeah. Any other questions? Yeah, that's the amount of iterations we train for our data set. So if we're training like a cat and dog classifier, we have like 100 cat images and 100 dog images for 200 images. The amount of epochs would be the amount of times we go through all 200 of those images. So if we do like if we go through all 200 of them 5 times, we're training it for 5 epochs. Yeah. And then we have double descent, which is kind of like a phenomenon while training. I can honestly I'll show this little demo here in a sec. All right, so initially what we're used to is kind of this first half, right? Where as we're training the model, the train curve and the validation curve is going down smoothly, right? And then at a certain point, right? First of all, let me just explain the graph actually. That'd be a better idea. Right, so we have a graph, right, where we have the prediction error mapped as a function of the model parameters, right? The model complexity. So on the right, on the bottom, as we increase the model parameters, we're going to see kind of like a reflection of our prediction error. We want it as low as possible, right? So, I mean, intuitively, we're going to see, okay, our prediction error goes down as we add more features to the model. But at a certain point, again, when we add more features, right, we're going to see that validation error kind of start to shoot up, because now we're just memorizing, right? We're having a really complex model for something that might be too trivial, and it's just starting to memorize data and not actually generalize, right? And so it gets to a point where we're overfitted to kind of like a very large degree, and that's called our interpolation point, right? That's when our training error is basically 0, but our validation error is crazy high, and that's because we've only memorized the data, right? And because we have so much parameters in our model, we're not really doing any learning. But what happens here is there's kind of like a phenomenon that's found commonly through research, is that that validation loss starts to come down as soon as we even increase it even more, right? So our model parameters are really high here, but if we go a little bit more, we might see this trend where the prediction error actually starts to go down, right? So it's kind of like a walking contradiction as to like what's happening here. And the reason for that is at a certain point, if you had so many features to a model, so many parameters, so much complexity, right? At a certain point, it's going to forego that amount of learning to like trying to map every single thing to trying to pick the most simplest solutions, right? That's when you start to see, okay, the model is actually going from generalizing to memorizing, and now it starts to generalizing again, right? And it's going to have this decision boundaries that are simpler, right? And that's just going to benefit for us when we see that validation curve, right? So the training curve doesn't really change here. We're still going to see that zero loss, but internally, as the model gets better at generalizing, our validation curve is going to go down, and that's what we call double descent. Is a double descent in our validation curves. And honestly, I mean, we might even see it more than twice in certain scenarios. So here's just a walkthrough. I mean, yeah, so as we go over plotting the training and testing error against some measure of model complexity, say training time for a typical case might look like this in this figure, right? We see it decreasing, which is what we want, right? And then we hit the concept of the classical bias and variance trade-off, right? As we move across, we overfit, and we expect the test error to skyrocket, right? And then there comes a point where it comes down. It has achieved its best performance, and it does so using the second descent, right? And this is usually better than the first descent, which is why this is good in a way, right? And so we call this parameterized regions to the left of the second descent the classical regime, and the point of a peak error the interpolation threshold. Just a lot of terminology, honestly. Yeah. Yeah, so that's what it is, double descent. We have our validation curves going down again, mainly because the model is starting to generalize instead of memorize. Okay, we have this other concept called grokking, which is the neural network learns to generalize unexpectedly after overfitting. This one's a little less common. So this is where we have specific scenarios. This is way less common, again, than our double descent. And we shift the model from memorizing to simpler and more generalizable judgments, right? And here we have the graph. You can see we have the optimization steps, which again would be correlated to the amount of epochs, right? And how much we're training the model. And at this certain point, when we're at 1,000 optimization steps, you see our training accuracy 100%. We're not making any errors during training, but with the little validation curve, you see that there's 0% accuracy because we've memorized that data, right? But once we continue training it, we start to see that the model, again, opts in for these simpler and generalizable judgments, right? And so what we're seeing with both of these is that there's kind of an idea where at a certain point with model complexity, as well as the amount of time we train the model, we overfit it. But if we kind of go for even further in certain scenarios, we might just start to see where the model naturally behaves in a way where the error starts to go back down again. And we kind of have this trend where it might perform better than it before it was overfitting. Okay, so why should you always train a neural network from scratch? Does anyone know why? Anyone know why? No? This is a trick question. You shouldn't. I mean, kind of going into our next topic, transfer learning, you absolutely should not have to train a new model every single time. I mean, I'd lie to you if I told you I remember the last time I actually trained a model from scratch. A lot of times you're either implementing other models, you're testing them, you're working with them, or you're doing something called what's transfer learning. And this is the idea that we're using an existing architecture that we know already works, right? And we're just applying it to another problem, right? So let's say we have a neural network that classifies cats and dogs, right? We could technically use the same architecture, right? Because at the end of the day, we're kind of classifying images, and we could use the same architecture and apply it to something else with different images, right? So let's say we have cats and dogs, but now we could use that and apply it to, I don't know, differentiate between chairs and tables, right? I mean, obviously it's not the same problem, but at the end of the day, the core way the model learns in the architecture is going to stay the same, right? So that's usually one of the best things when learning the model is to try to look at other architectures and see, okay, hey, can I apply this, right? Obviously you don't want to go ahead and just steal the model, but you want to appropriately use some of these open source architectures like ResNet 18, like we discussed before. And kind of what we do is we apply transfer learning. So transfer learning is the idea of using pre-existing deep neural networks and training certain layers, usually the end layers. We want to pick the layers that we refrain from training, right? So in this little diagram, the pink layers or the pink neurons are the ones we're going to freeze. So we're not going to update anything there, right? And you may ask, why don't we want to update them? Why don't we just retrain the whole thing? We have the architecture. Well, it saves us time and it saves us computation space, and the model's not going to be much different if we just freeze those layers and save us time and space, right? So we freeze those layers, we can't backpropagate them, they can't be updated, right? And then we add some custom layers if needed, right? We can maybe add these custom layers, we could maybe freeze some layers and retrain them, right? There's a whole lot of leeway with what we can do there. We can utilize different output layers to match our model purpose, which is what we usually want to do, right? If we're doing cat and dog classification, that's a classification of two classes. And if you want to do chairs and tables and let's say, I don't know, pencils, we need three. So we're going to have to change that final layer regardless. But I mean, at the end of the day, it still works. I know for our class project that we did for machine learning engineering, we used ResNet 18 to kind of classify between different types of, I think it was stationary objects, laptops, pencils, backpacks, right? So the model architecture was designed for a completely different purpose. We had like only 1,000 images. That's another benefit of transfer learning, right? Although the model isn't really storing like data, right? It's only, you only have its architecture. You can still benefit off of the fact that the architecture already has preloaded weights on these neurons, right? So we don't need as much training as we would need if we were just to do it from scratch, right? So if we were needed to train like a model to detect cats and dogs, right? And we use ResNet 18 instead of creating our own from scratch, we might only need like 1,000 images instead of like 100,000, right? So that's another huge benefit besides time and computation. Um, and yeah, so getting into our little demo here. Um, this is an MNIST dataset demo. So what we're going to do is we're going to kind of see how we build a neural network. This one's from scratch, but we can kind of play with it too. Let me just clear this. Let me just reconnect this first. Are you guys familiar with PyTorch, scikit-learn, some of the Python libraries? Yeah? No? Okay. Don't worry. I know some of this might be a little intimidating, but it's very intuitive. If you look at it from a simple aspect, and I don't think you need to like memorize every single thing. But I mean, the first thing we usually do is we import all our libraries, right? Whatever we need. Usually, I mean, you don't have to memorize this at all. What this is doing here, device, is we're setting the device in which we're going to do the training on. CUDA is our GPU, right? So if we're doing CUDA, if torch.CUDA is available, so if we have a GPU available, we're going to use it. Otherwise, we're going to stick to the CPU, and then we're going to print the device that we're using. So if we run that cell right there, have you guys used Jupyter Notebooks or any sort of like notebook system? Yeah. Okay. For those who haven't, this is basically, I mean, you're probably familiar with like a Python file and like your Visual Studio Code or whatever. Basically here, we're just breaking it down into chunks, right? And we can run each individual cell or block of code, right? So this is just the import cell, right? And we can rerun it as many times, right? If I go down and I'm training a model and I realize, oh shoot, I need torch dot, I don't know, random classifier, I can just import it here, right? Run it and then go back to where I was coding before without having to update anything in between. So that's the biggest benefit with that. That's basically what that is. Notebook's very similar to just a regular Python file. It's just broken down and you have headings. It's some cool stuff. But okay, so we have our device loaded up and ready. We're gonna load our MNIST dataset. We're gonna download it from datasets.mnist, so it's already preloaded in the Python packaging. We're gonna save it. We're gonna have this one set to training. We're gonna have this one not set to training, right? And we're gonna have this thing called a transform. So we're gonna basically pass in what is kind of like a transformation to kind of convert all of this onto a tensor. A tensor is basically kind of like a fancy word for like kind of like a vectorized array where we can train it on a GPU and kind of track its gradients and everything. You don't need to get too detailed into that. And then we have what's called a train loader, which is basically what we're going to use during training. We're going to use that to pull our data, right? So we loaded the data into our kind of like our directory, and now we're going to load it into this thing called a train loader, right? And here we can specify the batch size, how much we're going to pull at each time to update or make iterations. We have a shuffle feature, right? which is set true for training, but not for testing. Does anyone know why we want to shuffle our data for training, but not for testing? Anyone have any ideas? Yeah.
Is it so it doesn't memorize the data?
Yeah, exactly. Right. So if we're gonna have a shuffling during training, the model can't memorize its order, right? But during testing, we really don't care because at inference time, we want kind of like the natural distribution of our data, right? So here, everything should be loaded. All the outputs are saved from before, so don't mind that. But everything's loaded, and then we define our model. We're gonna stick to something very simple. We're gonna have a model, right? And we're gonna define it using nn.sequential, which is basically a fancy term for stacking layers. We define these layers. The first one is a flattened layer. So we basically have, right, images. MNIST data set. Let me just Google and show you guys what MNIST looks like. Right, so we have these data images, right? And these are like square images, so they have a dimensionality to them. They're like what, like 226 or something by something. So they're like, let's say they're 5 by 5. What we want to do is we want to flatten them, right? So we have something that's not 5 by 5, but just straight up 25 pieces of data, right? So that's easier for our neural network to kind of go through. Later, what we want to do is convolution. We're going to have something called convolutional neural networks. We're going to have like little sliders of boxes and like a different structure of layers. But that's something for a later lecture. Right now, we're just going to flatten the whole 2D dimension structure, two-dimensional structure into something that's one-dimensional. Then we're going to have 784 neurons into our first layer. This is like the first transition of 784 to 128. That's our first layer. Then we have our second layer where we have 128 incoming neurons to map to 10 different neurons, right? Why 10? Because we need to identify 10 digits, right? So, I mean, we could easily make this more complicated if we want to make it like 256, right? We could add something that does, okay, 784, right? So the second layer is 256. Now we could take in something that's 256 and do 128. Boom, we added more complexity to our model. Right, and then we have our activation function, ReLU, which, as you guys might have seen before, it's kind of like just, I think it's like a piecewise function between 0 and some certain value. I don't remember, actually, let's just look it up. Don't remember exactly what it is. Yeah, so we either have 0 or a certain value. Usually that's what we have. We can opt in for some regularization. We can put in leaky ReLU. But for now, let's just stick to what we had before. We'll play with this later. And then we have criterion, which is how we're updating our parameters, our loss function, right? So we have cross entropy loss, which is something we use for multi-class classification. Not to be too detailed about it, but it's basically kind of like how we have mean squared error, like someone mentioned before. This is just another version, but for neural networks. And we're basically trying to have a gradient through this and trying to optimize that. Then we have an optimizer, which is basically how we're going to be updating stuff, our learning rate. So Atom is a very popular one, and it basically micro adjusts the learning rate based off of our momentum. So if we have really good momentum with our training, it's going to increase it and make micro adjustments there. You don't have to learn the mechanics for that. I personally don't know the full mechanics for that. I just know Atom is probably the best one. There's another one, stochastic gradient descent, but it doesn't have that momentum feature that Atom does. And then we're going to print our model. So we're just basically going to see what we have here with our sequential structure of layerings. I mean, if we were to go back and kind of see, it would look like something like this, where we'd have 700 whatsoever layers, neurons there, 128. Anyone have any questions so far? No? Okay. And then, okay, why are we defining our loss and optimizer again? Maybe we should be doing that in a different cell, not here. Okay, so we move that criterion optimizer here, just move that line to here, different cell. All right, so now we're gonna actually kind of train our model. We're gonna train it for 10 epochs. And we're gonna see, okay, so we're gonna do for 4 epoch and range epoch, simple for loop. We're gonna set it to a model to train, right? basically now the model is in the mode where we can update its weights and everything. And what we're going to do is we're going to have another simple for loop with 4 images and labels in train loader. That's the good thing about a train loader is we can just establish a simple for loop with that. And we basically, next thing we do is we put them on our device, our GPU, right, for better computation. We zero the gradient of our optimizer because the optimizer, what it's doing is it's tracking our gradient, and we want to zero that. We don't want to have anything from before saved, right? And all of this is interconnected. So as soon as we do the output of the model and the batch images, the next thing we do is we calculate the loss using our outputs and our labels, and we take a step back with our loss. That's basically the back propagation of our gradients. And then we step with our optimizer to adjust all our hyperparameters. And that's a single batch right there. And for every single batch, we iterate through all the batches. And then at the end of every epoch, we output the loss, right? And if we train this right here, we should see something where the loss goes down and down and down. If not, that's going to be embarrassing, but it's whatever, I guess. It's taking a while. Okay. So we're seeing the loss kind of oscillating at the start. It's going down. We want it to go down smoothly. We don't want much oscillation. It went back up, not really ideal. Yeah. Okay. So, I mean, right now what we have is simple neural network up and running. I mean, obviously it's not going to be perfect. Again, there's only like 2 layers. Like we saw before, that really doesn't end so well. We're gonna add more complexity, a lot of tuning, right? And so that should help with that. Let me just wait for this to finish. Okay, so the final loss is actually the largest loss. So our training did absolutely nothing. Perfect. Okay, so we're gonna examine our model. What the previous line did is we basically grabbed all our labels from our our test set, right? So the first thing we did, we set the torch to stop tracking gradient, right? We go into our test loader, and we get all the images and labels. We predict the output, right? And then we do this line in which we're getting proper classification, and then we extend all the labels with the previous labels. So now what we have is all the labels and all the predictions. And what we can do then is we can have a little confusion matrix and kind of like a little bit of evaluation. I'm not going to go over the code mainly because I don't think it's that important to what we're doing right now. This is mainly just a confusion matrix. And what a confusion matrix is for every single, this is not very nice. It's kind of hard to see, but let me just look up a better confusion matrix that I can show you guys. Actually, this is not what I want either. Right here. Okay, perfect. Right? So this is from a flower prediction problem, right? So what we have is like we have all the classes, the true labels of all the classes here, and we have the predicted labels right here, right? And basically, we're going to see, okay, for every single time where we have Setosa as a true label, how many times did we predict it correctly right here? How many times did we predict it as the first wrong class? And how many times did we predict it here? In this case, all the times this lined up. So ideally what we want is if all our predictions work correctly, it should look like an identity matrix where we have all our diagonals have like crazy high values, something like this. Obviously, I don't expect it to be 0, 0, 0, 0, 0. But basically, if we look at something like this, if we grab a random spot from the matrix, like if we have versicolor or whatever right here, that's our true label. But if we predicted Virginica, right, we want to see how many times we did that. We didn't do that at all. So that's good, right? And we want to see, okay, versicolor, and how many times we predicted that right. We see it right here. We predicted it all the times correctly. So that's what's going on here. I mean, you saw already our loss was kind of crazy, but it's actually performing pretty well with our confusion matrix. So there's still learning that's happening. I mean, although we messed up on that last iteration, there was still an update of weights that allowed us to reach here. And then we can also look at the correct and incorrect samples. Yeah, so this one, the model predicted correctly, right? We have a 7 right here. It was a 7 and it predicted a 7. And then we have an 8 and it predicted a 2. I don't know why it would do that, but something like this, where it predicted a 9 instead of a 4, you can start to see why from maybe a human perspective that might be happening. So you can certainly see that if the model doesn't have a large amount of complexity, it can certainly make misjudgments like these. So we're gonna kind of go back and see if we can improve this model. Does anyone have any suggestions from the slideshow that we can make? For every suggestion that works, Alvin's gonna give out a little prize. Any ideas what we could do? Yeah.
Add more layers.
Yeah, certainly we could add more layers. So we have 784 incoming here. So this layer is 128. How many do you want to change that to? Okay. And then for every layer, we need obviously a loss function. I just auto-completed that. There we go. Vibe coding right here. This one has 256, so this one's 128. We can also do more stuff. Anyone have any ideas we could play with? Yeah.
I don't know if this is right, but you could change like lower your learning rate maybe, since it's like making big jumps and oscillating in the loss function.
Yeah, that's something we could try for sure. I mean, again, with something like this, I hate to say it, it might be like a guess and check unless you've trained so many models, like these types of models. You just have to play around with different values. That's why we also have hyperparameter tuning, where we tune these different types of parameters that are not really related to our model actually learning directly, but they're actually just kind of relating to how it's learning. So if we want to make it learn lower, right, at a lower rate, because right here we're just seeing it oscillating, we could definitely try that. I mean, also you could attribute this to like, hey, maybe like it's jumping too much because there's not enough momentum that we're gaining, right? So maybe if it's not lower learning rate, maybe it should be a higher learning rate. We also don't want to make too many changes at once, unless we're sure of a change. Like something like, okay, if we have 2 layers, then obviously you should add a 3rd layer. That's not something crazy, but we also don't want to like increase our learning rate, lower our epochs, add more data, and just like do a bunch of stuff, and then it improves, but we don't know why it improved, right? So we want to be smart with that. Any more suggestions in the slides? I can make a little change right here, if you guys don't mind. I'm gonna add leaky RLU. Maybe that helps, maybe it doesn't. And another thing, I think our batch size was a little, maybe, I feel like that should help too. Not really fan 64. Let's rerun it. Let's see what's going on. You could also track our accuracy, because I know loss is a little ugly to look at. Kind of want to look at something that's a little neater. So, okay, we're starting to see our loss go down a little better in a way, I guess. Never mind. So maybe something was not smart addition. The actual accuracy for the MNIST dataset using like a model is like, I think it's like 100%. So you can actually achieve like 100% accuracy. I think it was 98% recently, but then they went inside and they were like, there's something wrong with the data set. So they fixed that. Apparently you can get 100% accuracy with this data set if you use like the appropriate neural network, which is a convolutional neural network specifically for optimized for images. But as we see here, our loss is actually getting better. It's converging nicely. So the recommendation of reducing the learning rate was actually spot on. Never mind. Um, Actually, maybe reducing the batch size made it worse, probably, because we're seeing less samples at each iteration. Okay, so overall, we should see better performance. I mean, this is our confusion matrix before. Let's see if we have a better identity matrix. I should have, did we, do I remember? It's 97% accuracy. I actually don't remember the previous accuracy. Still crazy good, I'd say. But let's see if we can make this better. First thing we're gonna do is change back what I had earlier. I think 3 layers is good enough. If we could do. What if we track our training accuracy? Let's see.
What if you increase the amount of defaults? Would that make it better?
We could do that. As a matter of fact, we should probably plot this so we can actually see what's going on. Let's double the epochs. Let's track all our losses. We changed it back, we increased the batch size, right? So at each optimization step where we update the model, we're gonna have more images instead of just 32. We doubled it. So we should have more validation with what we're doing. Again, the loss starts off pretty low. I feel like I'm gambling right now. Just like waiting for my. Okay, it's going down 0.009. How would I deal with want to be? Usually we could have usually what we would have is a validation curve, which is what we would see in the slides, right? This is not included here. I mean, I could add it, but to save the time, I'll just explain. The whole point again would be to kind of track that progress and without actually using the training data and update our hyperparameters, right? That's the whole point. We have hyperparameter tuning. It's getting slightly better. I don't know if we're gonna get better than that 97% mark, but I think they do something like this in the NVIDIA deep learning workshop, which should be coming out pretty soon. I think last year was in November. I went to 2 sessions. So if you guys want to go, I would recommend going to it. I think the first session they had free pizza, so I mean, worst comes to worst, you can just grab free pizza. But it was pretty good in the sense that since you guys already have this idea of neural networks and stuff, you can kind of have your best foot forward. And the guy who runs it is obviously way better lecturer than I am. So he kind of also plays with the MNIST data set, but he also plays with some of the convolutional neural networks. And if you guys want, I think they should have, UF does have a system where you guys can do some of the self-paced NVIDIA workshops. So if you're really into just kind of going back on this, you could restart the deep learning, fundamentals of deep learning. If you want to learn more about LLMs, you could do that. So it's just a tip right there. Let me add a cell to kind of plot this loss, which I don't know how to do. So I don't know how to use matplotlib. So perfect. That should be good. Wait, do we have to accept it too or something? Not really. I'll accept and run. Oh wait, no, we gotta wait for that to finish. My bad. Okay, perfect. So I mean, we see here this is not what we like ideally. So I mean, it's still going down. If we had like a little best fits line or whatever, we'd see that the loss is definitely going down, but it's definitely still spiking. The learning is not very smooth. Again, there's more things we can keep playing with, but for the sake of y'all's time, I don't want to keep you here. You could increase the bat size. I mean, you could definitely, I don't think training for mirror epochs would be beneficial, mainly because we're already seeing it to plateau over here. We want a better and smoother convergence so we can kind of have more precision. And so if we're aiming for more precision, what we usually want is just, again, like he said, lower, maybe like a lower learning rate so it updates slowly but precisely, a higher batch size so we're taking more valuable steps at each iteration, accounting for more images. I don't think model complexity is really going to help here. But yeah, that should be it. Let's see if the model got better. So it actually did get better. So it's 98% accuracy now. There we go. These are a bunch of metrics: precision, recall, F1 score. You can quickly go over them, honestly. I don't have them memorized. Right? So these are just a bunch of formulas. You don't have to memorize them. Obviously, I don't have them memorized. But precision is basically the amount of true positives, right? The amount of samples we're predicting correctly, right? Divided by the true positives and the false positives, like the sum of the true positives and the false positives, right? So we're basically looking at how many times out of how many positive predictions, how many of them are actually correct. Recall is we're looking at true positives plus false negatives. So out of the actual positive values, how many of them were actually positive? How many of them we recalled correctly? Right? So kind of their name intuitively leads us to precision is how precise are we with our positive predictions? Recall is how accurate are we in general with recalling the right values? F1 score is a combination of precision and recall with that formula right there. So we kind of have like a balanced look at both of them. And accuracy is just in general, what are we getting right on all the classes, true positive and true negative. And the reason we want to use precision and recall mainly is because sometimes when we train a model, if we have, I think Alvin went over this in the first lecture, if we have something where, let's say we're predicting credit card fraud, right? Credit card fraud happens like probably like once every so many thousand times, right? And if we have a machine learning model that goes off of that data and we just set it to predict false every single time, and it's going to have like a 99% accuracy rate, right? Because honestly, if we miss those fraudulent detections, our accuracy rate is still going to look really good, right? Because fraud doesn't really happen that much, right? But we still need, the whole point of the model is to detect those instances where fraud happens, right? So that's where precision and recall comes into, right? If we were to look at those values, our precision and recall values would be much different than our accuracy values for that credit card fraud detection. So that's a little tidbit about that and why that's important. Usually, I would say for neural networks especially, I think both metrics are really important, but especially if you have class imbalances like the credit card fraud detection, you want to be sure that you're looking at both the precision recall and the F1 score, in which our case, everything's pretty high. So, yeah.
In this case, like for each image, you can predict like all the different digits. So what would be considered as a positive?
So like a true positive, well, this one would be for like each individual class, right? I know like, so it's not binary classes. So just would be like in the total, like the overall true positives, right? Like how many times did we predict, okay, if this is an 8, we predicted an 8, right? Or if we predicted an 8, but it was actually a 7, that would be a, depending on what that was, whether a false positive or a false negative. Yeah. But yeah, so I mean, yeah, usually in this sample they explain it with binary classification, but this can still apply to a lot of classes as well. Uh, yeah, I think that should be it. Uh, yeah, that's it, guys, today.
Stop the stream.